Hi everyone. Today we are going to talk about vacuum pumps and the vacuum system that goes into generating the vacuum, the ultra high vacuum conditions that are necessary um, for both the scanning electron microscope and the transmission electron microscope. And in fact, what we're going to discuss today is true for any ultra high vacuum system, be it an X-ray photoelectron spectroscopy tool or a deposition tool that you might use in your research, or you may come across, for example, a sputtering system or a pulse laser deposition system or any other vacuum system that requires pressures that are in the 10 to the negative 7 or 8 torrs, which is generally considered ultra high vacuum, right? So here is the schematic. We have seen this image in the past. We are going to focus on the pumping system right here. And as I said, the vacuum system for both the TEM and the SEM are similar. So let's just jump into it. So typically the pumps are essential to generate the vacuum in the electron column. And as you can already guess, if you're unable to generate good vacuum, you'll end up with getting contaminants, which could be hydrocarbons or water vapor on your specimen. And as we have seen, there are several techniques, for example, the X-ray photoelectron spectroscopy or Auger electron spectroscopy, or even if you are interested in looking at secondary electrons, the quality of the surface of your specimen will determine what kind of data you get. So if you have the surface of your specimen with a coating of water vapor or hydrocarbon, which is simply because the room you're working on has a high humidity, and then before you loaded the sample in your vacuum system or in your electron microscope, there was some water, a thin film of water on your sample, and then you put it in there, but the vacuum system in the electron microscope wasn't good enough to desorb the water molecules from the surface of your sample, so you will end up getting poor data, which is why it's important that you get a really good quality vacuum to get rid of contaminants. And also think about it, if you don't have good vacuum in your electron column, this water vapor, the layer of water vapor or hydrocarbon is going to accumulate over time on your electromagnetic lenses, your aperture and stuff. So as I said, this is probably one of the most important aspects of any ultra high vacuum system, especially any imaging system that relies on the proper transmission and collection of electrons. The general unit or the SI unit for pressure is in pascals, but usually in the industry and also in research, torr is very commonly used. Bar not so much, maybe geologists do that, but not amongst physicists. So you will see a lot of torr or millitorr conversations among physicists and engineers. You can broadly categorize vacuum as rough vacuum, low vacuum, high or ultra high vacuum, and they are categorized by the pressure ranges mentioned here. So a rough vacuum would give you anywhere between 100 to 0.1 Pascal. Low vacuum is 0.1 to 10 to the negative 4. And then you enter the regime of high and ultra high vacuum with the respective ranges over here. Just want to lay out that the vacuum system itself can be really expensive. So it's a lot like horses for courses, where depending on the kind of filament you're using, you're going to choose the appropriate vacuum system. So think about it. If you have a thermionic filament, then you're probably okay in the 10 to the negative 4 to 10 to the negative 7 Pascal. But if you're using a field emission gun, then you definitely need to rely on an ultra high vacuum system. And as I said, any surface related phenomena that can be affected by surface contaminants, as STEM or XPS or AES, you need ultra high vacuum. Okay, and over here in the box I have laid out some basic conversion relationships, just for your reference. So the whole idea of this lecture is to make you familiar with the different kind of pumps and the vacuum lines and systems, the basic principle of how a vacuum pump works has a lot to do with mechanical engineering, electrical engineering. Also, a lot of thermodynamics and kinetics go into understanding and optimizing the molecular flow of atoms and gas molecules. And this is technology that has evolved over decades, maybe over 50 to 60 years. The first electron microscopes were probably operated in the rough to low vacuum range, but the high and ultra high vacuum technologies have evolved probably even longer, maybe 80 years now. So it is impossible to capture all of that in a lecture on electron microscopes. So as a user, what I expect is you are familiar with what are the different microscopy techniques, the vacuum pumps, and how you would choose your vacuum setup depending on what kind of electron microscope you desire to use. So the whole idea is, let's say you want to order an electron microscope, and you want to figure out, hey, I got this electron microscope, what kind of vacuum system do I want with it? Because usually you can customize it. And then you would know that, okay, if it's a field emission gun, I need to rely on these pumps that have these properties, and we'll talk about those in the subsequent slides. Also keep in mind that the general pumping mechanism, as an operator, you will need to have a few thumb rules and guidelines you need to follow, because if you don't, then you will end up ruining the vacuum system altogether, which will which will be a severe problem, because you can end up damaging your electron gun, and the vacuum system itself. It's tens of thousands of dollars. Okay, so let's get into what is a roughing pump. The name is pretty straightforward. This is a pump that will give you a rough vacuum, which is categorized within this pressure range, right? And one of the most common roughing pumps are what is called a rotary vane pump. As you can see here in the schematic, I'll get into that in a bit. These pumps are really good for pumping down from atmospheric pressure. So you're at atmospheric pressure, you've just started pumping. The first thing you would do is turn on the roughing pump to bring down the pressure in the chamber and in the lines to the lower limit, which is about 0.1 Pascal. They work great with low viscous fluids. Usually gas molecules at room temperature in atmosphere can be categorized as low viscous fluids. And then there are different variants of a rotary vane pump. You can have a hydrocarbon oil based, or you can have air or dry pumps. And if you see in our department, if you do any kind of research, you will definitely encounter one of the two. The air pumps are a bit more expensive compared to the oil-based pumps. And usually they are not kept within the TEM or SEM room if you're using, let's say, a field emission source or a thermionic source, because these pumps are mechanical, so they generate a lot of vibration. And if you're doing sub-nanometer resolution measurements, then definitely you want to isolate that vibration from the room completely altogether and have long pumping lines so that you make sure that the vibration does not interfere with your measurement itself. Okay, let's take a look at the schematic over here. So you have, so this is the core of the pump, which is the white region is your pump chamber. You have the inlet port, so this would be connected to the chamber you want to pump right here, and the outlet port is something that is the exhaust, which is just going out, preferably into a the HVAC system of your building, so that you don't breathe the air. And the basic thing is you have, so this thing looks like a disc over here, but this is actually a barrel, right? So the yellow disc that you see here is actually a cylinder, which rotates, and it is positioned off center on purpose. right? So it is not in the center of it. And then you have this rotary vane, which is a metal plate. Again, think of it in 3 dimensions. So this has a third dimension that is going into the screen. So that's a metal plate that grazes along the circumference of the barrel here, right? So what happens is, as you're pumping, so this is rotating, it collects the air from the inlet port, and while it is rotating, because it is off-centric, that same air, the amount of air that it collects in one revolution, gets compressed further into a smaller volume, thereby increasing the pressure, and then it goes out the inlet, out the port. Okay, so this will become a bit more clearer if we look at this video. There are very nice schematic animation tools online. Okay, let's see, how do you play this? Okay, there you go. So this is what I was talking about. You have a certain amount of air that's coming in, and the rotary vane is compressing the air into a smaller volume, thereby increasing the pressure, and it gets out of the exhaust valve, right? And then one of the features of this kind of barrel-shaped circular cylinder pumps is that there is a lot of friction between the inner wall of the vacuum chamber, the pump chamber, and the cylinder here. So you need to have that lubricated with oil. Usually these are hydrocarbon oils. They are standard available in the market, and the oil have a very low vapor pressure. Certain advantages of a oil pump: one, it's very inexpensive, so it's much easier to install and maintain. You just need to change the oil from time to time. It's similar to doing an oil change in your car. When you take it to a mechanic, you just drain the old oil out and pour new oil in it. The disadvantage to that is you can end up getting oil contamination into your vacuum chamber if you're not careful on the way you pump down your chamber, and we'll get to that right before we discuss ultra high vacuum system pumps. So one other variant of the rotary vane pump is where you don't need the oil at all. So that's a dry pump, right? And let's take a look at how it works. So let's see. Okay, so this is your dry pump, and instead of the barrel, now you have these discs, these plates that have variable. They have these are spring loaded, so the disc actually compresses or extends depending on which part of the of the rotation cycle it is in. And the whole idea is that you get rid of the cylindrical barrel that was rotating within the pump. Instead, you just have these blade kind of things, and you can see here it is taking the air from the right hand side, and then it is compressing it. So the air that is held within a certain volume gets compressed. Obviously it gets the pressure increases, and so the air exits from this end. This is the very basic air rotary vane pump. Okay, now let's move on to the ultra high vacuum and high vacuum pump systems. Broadly, they are classified as diffusion pumps, turbomolecular pumps, ion pumps, or cryogenic pumps. I think in our department you will find turbomolecular pumps in various systems. There is a cryo pump in the sputtering tool, so maybe you can take a look at that. I can direct you to that. I think Sarah knows about it probably, because Dr. Ame is one of the users of the sputtering system. I don't believe we have ion pumps, or maybe we do. I need to check that. Anyway, so those are the 4 classifications of high and ultra high vacuum pumps that will give you the pressure ranges as we discussed earlier. And before we get into that, we want to talk about certain procedures in the procedures you would adopt while pumping down a chamber from atmosphere. Okay, so generally your system setup will have a certain number of mechanisms and valves and lines that you need to be aware of. So let's take a look at this system here. This is just a schematic. That's your chamber. In our case, it would be an electron column, right? And this is true for any ultra high vacuum system setup. And here they have described a diffusion pump, so you can replace that with a turbomolecular or an ion pump or a cryo pump, doesn't matter. But this is the pump that is responsible for ultra high vacuum. Okay, and then you have the mechanical pump, which is the rotary vane pump that we just discussed, which is also connected to the diffusion pump. Now the whole idea is that you don't want to expose your ultra high vacuum pump to atmospheric pressures while pumping down. And we will talk about that later when we discuss these pumps individually. So what you need to do is you need to first bring down the chamber pressure to a certain value that is attainable by the mechanical pump, right? So you open the roughing valve. So now the mechanical pump can actively pump on the vacuum chamber right here, and you have to make sure that your high vacuum valve is closed, and so is the 4-line valve. Once you have achieved a certain pressure within the chamber, that is when you open the 4-line valve. So now your mechanical pump is pumping on both the chamber and the diffusion pump. But keep in mind, the diffusion pump or any other ultra high vacuum pump is not on yet, and the high vacuum valve is also closed. Then there is typically a pressure monitor somewhere here that tells you that you have reached the pre-vacuum conditions for the respective pump that you have here. Under those circumstances, you're going to close the roughing valve, and then you're going to turn on the diffusion pump or the ultra high vacuum pump, and then you're going to open the ultra high vacuum valve, so that the mechanical pump should not be pumping on the chamber anymore the moment you open the ultra high vacuum valve. And that is very, very, very important, because imagine if you were using an oil-based pump here and the roughing valve was open and so was the ultra high vacuum pump, then what would happen is, because the ultra high vacuum pump would eventually achieve ultra high vacuum, there is a possibility that it's going to suck out all the oil from your mechanical pump and then directly into the diffusion pump or your turbomolecular pump, and then completely ruin it. So things as like those have happened in the past. Fortunately not with me, but I've seen that happen, and that is dangerous. So these are the guidelines. You should never have the roughing valve open while your ultra high vacuum pump is operational or your ultra high vacuum valve is open, and you should never operate the ultra high vacuum pump unless you have achieved the pre-vacuum conditions by opening the 4-line valve. Okay. All right, let's look at what are diffusion pumps. Diffusion pumps are very, very commonly used in extremely ultra high vacuum systems for XPS or AES or even in TEMs. And the main reason for that is it is a vibration-free technique. So you don't have any vibrations whatsoever. And let's take a look at the general working principle. You have some form of an oil which is at the base of your pump, and then the pump has certain columns and cones. So this is in 2D, but think about it in 3D. So these are cylinders and cones that are inverted, so it looks like a Christmas tree. So the whole idea is you heat up the oil. So this is your electron column right here on the top. You heat up the oil vapor or the molecules rise up, and when they hit, so these are different stages. So let's say this is stage 1, stage 2, and stage 3. They come out of these vents on the sides, right? And while they're doing it, by the time they are coming out of the vents here, the oil molecules have attained supersonic speed, right? Now there are these gas molecules that are drifting right like that, and the moment they are hit by the oil molecules, they are immediately forced onto the surface. So they gain momentum, and they're forced onto the surface of the inner walls of your diffusion pump. Now the inner walls of the diffusion pump are kept cold with water cooling coils that are wrapped around it. So the air molecule along with the oil molecule immediately condensate, and then they drift down back into the reservoir where you have the oil, and that is heated back up and the process continues. And keep in mind that the diffusion pump needs to be connected to the backing pump or your roughing pump, which is maintaining a rough vacuum. So all the gas molecules that were impinged by the oil molecule, and then they slid down along the coil, along the walls of the diffusion pump while it is cooling, then are eventually sucked out by your backing pump. Okay. So typically, if you were to use a diffusion pump, you will not turn it on unless you reach at least 200 millitorrs with your backing pump. You need to make sure your water cooling supply is constantly on, because if that fails, the pump will fail severely and potentially can catch fire. So that is important to know. But as I said, these pumps are extremely popular. They are quite inexpensive because there is nothing fancy going on here. You just have a heater, you have oil, which is cheap, and then certain mechanism where you're redirecting the oil vapor in a downward direction, where it collects the drifting air molecules and then moves it down and generates a higher vacuum on the top end. Now, sometimes it's possible that you have these gas molecules, the oil molecules, that maybe can drift their way up into the electron column. So this is a fail-safe mechanism where you have a liquid nitrogen trap. So it will immediately condensate any oil molecule that may have moved upward direction. So that is important to make sure that you don't contaminate your electron column with the oil molecules altogether. Okay. Turbomolecular pumps are stark contrast to the diffusion pumps that we just discussed. These are extremely these are composed of extremely fast moving parts. So there's a lot of mechanical motion inside. Typically, this is how a turbomolecular pump would look. And if you take off the outside casing, you're looking at these blades that rotate at about anywhere between 20,000 to 100,000 revolutions per minute, which is extremely fast. And if you haven't seen a turbo pump in the past, in a lab or research setting, you've definitely seen one on an aircraft. Those are the turbojet engines, that are the turbines that are connected to the wings of any aircraft to generate that kind of suction. So essentially, what happens is you have these extremely high speed rotor blades that rotate. So those are called the rotors, and then you have stators. Those are not rotating blades but stationary blades, but they are at a different angle with respect to the rotor blades. So you are imparting momentum to the drifting gas molecules in the downward direction with these high speed rotor blades, and once the air molecule goes past the first rotor blade, then immediately the direction is changed with the stator blade, and so on and so forth. So a combination of a rotor and a stator is one compression stage or a compressor stage, and the rotor blade rotates with respect to the spindle, which is also rotating at the same RPM. Typically, you have a spacing of about a millimeter between a rotor and a stator blade in the vertical direction. These blades are extremely susceptible to mechanical damage if you do not take care of the pre-vacuum condition, as I said, with the roughing pump. So if you were to turn on this pump directly in atmospheric pressure, because there's just a gush of air molecules coming in, these blades are going to bend over and break, and that's colossal damage, because you lose a $10,000 vacuum pump in a matter of seconds. So it's important that the vacuum chamber that would be connected on the top end of the turbomolecular pump has already been pre-vacuumed by your roughing vacuum pump with a different line. And also, as I said, for the diffusion pump, here is your 4-line roughing vacuum. So you need to maintain a differential pressure between the top end and the bottom end of your turbomolecular pump. Okay. One of the advantages is that it is purely air-based, so there is no oil. So you don't need a liquid nitrogen cold trap. There is no possibility that you're going to damage or contaminate your specimen if you're using a turbomolecular pump. But on the downside, there is vibration, so you need to spend a lot more money on somehow figuring out how you eliminate the vibration of these rotating blades from the electron column itself. And there is technology that is available, but that just increases the price of the overall setup. Okay. Now, the next we are looking at ion pumps, and these pumps are also very, very commonly used in electron microscopes. Again, because these are the vibration-free, motion-free. There's nothing moving around here, and they work based on the Lorentz force that we have seen in while we were discussing the electromagnetic lenses. So let's take a look at the general assembly of an ion pump. You have a magnet. So this is your north pole and your south pole that encases the entire ion pump. So that means you have a magnetic field that's going from your north pole to the south pole in this direction. This is connected to your electron chamber on the top. And then you have these cathodes, which is basically ground, right? So you have titanium cathodes, one plate here and another plate here. Now think of this as in 3D, and now you have your anodes, which are basically also cylinders. So you're looking at a cross section. So you have a cylinder of your cathode, which is going in a circular fashion like that, and then this is your anode, which is also a cylinder but placed. So it's the axis of the anode is along the magnetic field. Okay. So when you apply a potential, what happens is that electrons are emitted from your cathode, and these electrons, because of the presence of the magnetic field, are already in their helical path, and they are confined within the space until they interact with a gas molecule which has drifted down from the top. Now, once it interacts with the gas molecule, let's say, for example, it's oxygen, the electron quickly loses its charge, and the gas molecule is now ionized. Now, when the gas molecule is ionized, it moves towards the cathode. And because the cathode is made out of titanium, these really fast-moving gas molecules, once they're ionized, they knock off a titanium atom from the cathode itself. So now you have these floating titanium atoms. Once this happens, the titanium atom interacts with oxygen or nitrogen and forms titanium oxide or titanium nitride, and then deposits itself onto your anode, because your anode is positively charged and your titanium was negatively charged, right? So it traps these gas molecules along with it in the form of titanium oxide or titanium nitride. Nitride in the case if you had nitrogen atoms or nitrogen gas in your electron column. Okay, so as I said, there is a process of chemisorption, which is the formation of these titanium oxide or titanium nitride compounds within the diffusion pump, and also keep in mind that there is an electrical attraction on the cathodes, which is also absorbing some of the gas molecules or gas ions, which were ionized by the electrons because of the potential you're applying with your power supply. Now, the ion pumps are great because, as I said, there's no vibration, there is no oil involved here. It's basically an electrochemical process going on, as a result of which the pressure in your chamber is going down, and the ion current itself sort of gives you an idea of what kind of vacuum you have. So if you have a higher current, that means your vacuum is pretty good. If you have low current, actually it's the other way around. If you have low current, then your vacuum is good. If you have high current, that means you have more gas molecules, so there's more ionized particles floating around, so you have a higher current, which means it's poor, so you have to wait until all the gas molecules are absorbed onto the anode before the pressure goes down. One of the disadvantages of an ion pump is that an ion pump works only once you have high vacuum. So you just cannot connect it to a roughing pump and turn it on and it won't work. So you need high vacuum conditions to use the ion pump to achieve extremely good ultra high vacuum conditions. So usually in X-ray photoelectron spectroscopy or OG electron spectroscopy, you need to get to 10 to the negative 9, 10 to the negative 11 torr, which is very, very high vacuum, ultra high vacuum, and you would use an ion pump in that case. Okay. Finally, the last ultra high vacuum pump is the cryo pump, which relies on basically absorption or trapping gas molecules on really cold surfaces. So if you think about the kinetic energy of a molecule, which is directly proportional to the Boltzmann constant times temperature, if you decrease the temperature, you're decreasing the kinetic energy, and that way you absorb gas molecules on extremely porous surfaces, typically made of charcoal. And then there are certain other components to a cryo pump as well. You have a cryo compressor, which is essential for reducing the temperature of the interior walls of the pump completely. And then using the cryo pump, you don't get extremely high vacuum. You get moderate, or you don't get you will not be able to achieve the higher end of your ultra high vacuum conditions. But this is good for high vacuum to maybe the lower end of your ultra high vacuum condition, which is why cryo pumps are very popular as pre-vacuum pumps for your ion pump. So you would use a roughing pump to use a cryo pump, or let's put it this way: you would use a roughing pump for the pre-vacuum necessary for a cryo pump, and the combination of the roughing pump and the cryo pump will be good to create the pre-vacuum necessary for your ion pump, because you need really good vacuum to begin with, using the ion pump. Okay, so let's take a look at this this last animation, which gives a good understanding of how the cryo pump works. So you have a cryo compressor which cools down the entire system. The entire pump is now cold, typically, let's say, anywhere between 50 to 70 Kelvin. If you're using a cryo compressor, if you're using a liquid nitrogen door, then you're limited by the nitrogen temperature of 77 Kelvin. And as the surfaces get cold, first you have water condensation, right? So this is right there. You have these water condensations, and now your nitrogen and argon condensations occur at lower temperatures. And finally, when you reach even lower temperatures, then your hydrogen atoms are absorbed. Now, as any material, there is a limit where you achieve saturation, then you will get poor vacuum. You need to do what is called a regen, which is basically heating up the system. And as you're heating it, the gas molecules come out. Obviously, you will do this when you're not operating the electron microscope. So you get rid of the extra adsorbed molecules that you saw in the last phase of the animation, and then you come back to the virgin state where everything is clean, and then you cool it back down. Usually you can keep the system cold for hundreds of hours before a regen is necessary, but if you end up getting poor vacuum, most likely it's because your charcoal filters over here that contain the trapped gas molecules are close to saturation. So you shut down the system and you begin the regen process, which is essentially just heating it up and connecting it to a roughing pump, which sucks away all the gas molecules that were trapped within the surface of your cryo pump. Okay, so in the next class, that's the end of this class. In the next lecture, I'm going to talk about different vacuum gauges, and why you would use one over the other depending on what vacuum range you are in. And so until then, bye-bye.